Hi everyone. This is your lesson 5.3 on sampling distributions. Today is Wednesday, January 29th, and you all have a snow day. So I thank you for taking the time to watch this and thinking of what we could do so we really don't fall behind, because my fear is that it's going to, well, right now it seems really nice to have a snow day. I can't argue that one. Down the road, it could bite us in the butt, and we run either short of time to finish what we need to finish, or you have no time to review. So that's why you're watching this. So what I thought we could do is maybe, if you could spend the time watching this, we'll basically go through all the notes for lesson 5.3. Hopefully you have the handout. If you do not, you might want to pause this and go get it in Brain Honey. It is there in the lesson 5.3 folder, okay? So what I thought we could do is maybe get through the notes, maybe do a couple problems. I think I only have 3 little ones that I'm going to ask you to do for homework after this. But then what we'll do is maybe come back after you have your quiz and really just spend more time on the problems. You know, you all might have heard of the concept these days of a flipped classroom. That's kind of what we're doing right now. You know, you're going to get the notes on your own via this video lesson, and then we'll come together later and just do more of the practice problems before you have the rest of the homework. Okay? So I thank you for taking the time to watch this. So let's get going so we don't take up too much of your snow day. You'll also want to have your textbook handy, please, okay? All right, so as a little opener, in general, there's 2 main ideas in this lesson. First of all, that a statistic is a random variable, and the value of which varies from experiment to experiment or from sample to sample. We've talked about the whole idea of a sampling distribution, and the whole idea that you have a big population, you're going to take lots of little samples and maybe find like an X bar for all of them and like average all those together. You know, we're still talking that same idea, right? Big population, lots of little samples, and compare what happens, okay? The random variable is going to have a sampling distribution, of course, with a mean and a standard deviation that can be calculated based upon little samples that you do. All right, so that's kind of the foundation of what we're still talking about. So with this chapter, you know, really the whole chapter that we're studying right now on statistical distributions, it's really getting us ready for that next step. Once we move into Unit 6, when we start talking about statistical inference. And we're looking right now at probability distributions of sampling distributions. And what statistical inference is going to do once we move there in the next unit is basically allow us to answer the question, how often would this method that I'm using yield a correct answer if I did it repeatedly? Now, sometimes though, depending upon the scenario, as I think you can imagine, it might not really be realistic to repeatedly produce your data. Think about, one of those common examples we've been talking about, having kids. Okay, well, you kind of can't repeat that over and over and over and over, really. I guess you could, but it's not very realistic. So this is where statistics comes in, is, okay, for those cases in which you really cannot actually reproduce your data, you need a way to kind of make conclusions and be confident that the conclusions you've drawn are correct, and then correctly use those conclusions to make predictions about the future. Right? That's kind of the step in which we're heading. This Unit 5 on statistical distributions is sort of that in-between ground getting us there. So to start with, we're going to review some definitions. And you might remember these way back in Unit 1. It seems forever ago for some reason. So a parameter, remember, a parameter is a number that generally describes the population as opposed to the sample. Remember, the p's go together. That's how we remembered it. Typically, you don't know the parameter, though, and you're trying to see if you can come up with an estimate for it. Remember one of them that we had, that mu? That's going to be the mean of a population. Remember sigma? Greek letter sigma was the standard deviation of a population, and we talked about how the Greek letters generally represent population values. And that is still true. A statistic then is a value that is computed from sample data and is used to estimate an unknown parameter. So a statistic is going to be related to your sample that you've collected. So of course the most popular, unknown parameter that we might be estimating is x bar, which would be our mean of the sample. And little s, remember, was our standard deviation of the sample. Now this third one is a big one though. Right, and it is something that we've talked about, and we've seen it in a lot of simulations that we've done. And we will actually do more simulations when we come back together again, whenever it is I see you again. As we've seen with some simulations is that when you generate one sample, okay, one simulation of something, and you calculate, for instance, x bar, okay, and we have an x bar value for that sample. Right, and then maybe we do another simulation and generate a different sample. Same size, same parameters and all that kind of stuff. But our x bar comes out different. Okay, that's what that third bullet's talking about, is the fact that even though we're dealing within the same population, the statistic you calculate from one sample very easily could differ from the statistic calculated from a different sample. All right, and that's one thing we've been talking about a lot. And we've been talking about how, our hope is, as we do, generate these samples over and over and over and over, hopefully there'll start to be some consistency at some point. Okay. We've talked about, for instance, in flipping a coin. We know the probability of getting a heads versus a tails is 50-50. Okay, and we talked about that long-term probability that you will, you might, if you only flip a coin like 3 times, you might get 3 heads. So you're thinking, I get a head every time I flip a coin. Well, we know that's not really right. It should be, if you keep flipping it, all day long, those probabilities are going to even out and reflect that 50-50 that we know theoretically it should be. All right, that's what that third item is about. So the statistic is also indicative of how the value of a statistic varies in repeated random sampling. That kind of goes along with the third idea. And that's where we have this idea called sampling variability. So this is something we've seen. We've never really just put words to it. And it's just the idea that, what we were just talking about, that if you have a main population and then you start generating little samples within that population, the statistic, so pretend we're trying to find the mean, okay, of whatever it is we've gathered. Our means could come out different, every time we take a new sample. That's what we refer to as sampling variability. All right, so let's talk a little bit more in depth about that. All right, and this is where, if you want to have your books out, we're going to use an example in our textbook. And this is going to be page 565, I think. Yes. It's example 9.2 that you'll see on that page. All right, so we talked about how little p, maybe we'll use that to represent the population parameter. Okay, whatever it is we're looking for. Okay, whether it's a mean or a proportion or whatever. So what we could do is from a population, of course, we can draw a sample. And maybe we could call p hat the sample statistic that we're going to use to estimate that unknown parameter p. All right, so let's take a look at this example 9.2 and kind of give this a little bit more context. So apparently the Gallup poll asked a random sample of 515 adults in the United States whether or not they believed in ghosts. So of the respondents, 160 said yes out of the 515. So the proportion of the sample who say they believe in ghosts, that's what we're going to call p hat, is the 160 over 515, so that's 0.31. So like 31%. One thing you're going to start seeing a lot more of is, we've talked so much about means a lot, almost exclusively. But now you're going to start talking a little bit more about proportions. Okay, so notice in this problem, we had 515 people we asked just if they believed in ghosts. Yes or no? All right, we're not trying to find the average number who believe in ghosts. We just want to know, out of the 515, how many believe in ghosts. That's a proportion. That is not a mean. All right, so one thing you need to understand as we kind of move forward, and this is going to come into play in the last two lessons of Unit 5 very heavily, is the difference between a mean and a proportion. A mean is like our quote-unquote average, okay? We can talk about average, mean salary, mean income level of families. We can talk about mean number of kids that a family has in the United States. All right, that's different from proportions, where maybe we want to know, okay, what proportion of women in the United States are teachers? What proportion of people believe in ghosts? Okay, there's a very much a difference between means and proportions. Okay, and that's what we're starting to kind of just delve into a little bit more. All right, so knowing from our sample here of 515 people, it seems like 31% of those people believed in ghosts. All right, that now becomes the statistic that we could use to try to estimate what the whole entire population of adults in the United States would believe about ghosts. Now, granted, we would probably have to do this a few times and maybe figure out the different proportions and maybe average them together. And that's what the second bullet talks about. If we were to choose a different sample, it's quite possible we won't get 31% again. We'll get something, maybe close, hopefully close, but it doesn't really have to be either. All right, so the idea that the statistic could vary with repeated random sampling, that's what we talk about when we mean random or sampling variability. All right, just the idea that, you got a big population, you're going to start drawing little samples and finding a mean or finding a proportion. And if you keep doing that repeatedly, the answers you get from those samples are going to vary somewhat. So, if we were to conduct a whole lot of simulations, think of the ghost example, okay? We got the whole population of adults in the United States. This particular sample was 515 people. Okay, well, suppose we started taking a whole lot of other samples and calculated that same proportion, p hat. We ask different size samples, and they don't even have to be the same sample size. Maybe we get a sample just of 300 at some point. Maybe we have a sample of 600. But we're always asking the same question. Do you believe in ghosts? So out of each sample that we draw, we're going to have a different p hat value that we arrive at. So one thing we could do, and this is something we'll do when we come together later and do the problems together, is we could create a histogram of all those p hat values and talk about the overall pattern, the shape, the spread, outliers. Socks is hopefully coming to your mind. And hopefully we're going to see a pattern emerge as we do that over and over and over. So the sampling distribution then really becomes the distribution of the values taken by the statistic in all possible samples of the same size. All right, so in this case, they are going to limit the size issue. That would kind of create a little bit more parity between the samples, so that does make sense. You know, and this is kind of how we described a sampling distribution back at the beginning of the unit. You know, it's really the distribution of values for a particular statistic if you were to consider all possible samples of the same size from the same population. And there should be, you know, an ideal pattern that should emerge. Okay, and we're going to take a look at an example of that. Okay, so on that same page we were just on, page 565, at the very bottom of that page, it's example 9.3 about checked baggage. They actually kind of did what we were just talking about there. So they're talking about travelers passing through airport in Guadalajara, Mexico. Before leaving the airport, each passenger, of course, has to go through customs. If you've ever traveled out of the country, you know that. Custom officials want to make sure that the passengers are not bringing illegal items into the country. But they don't necessarily have time to search every single traveler's bag. So they basically, you know, they pretty much, the way they describe it here, it's like, I don't know, kind of archaic. So you go through customs, you hit a button, and when you hit the button, if the light turns green, they're going to check your baggage. Otherwise, if it turns red, you get a pass. Okay, it sounds a little strange, but that's what they're describing. Oh, green means go, so you get a pass then. That makes sense. So if it's red, they're going to search your bag. Okay. So they're not going to search everybody's bag. They're going to search a sample of bags that come through every day. So if you flip to the top of the next page, it says that custom officers claim that the probability that the light turns green on any press is 70%. So if you think about what that means, okay, so if the light turns green 70% of the time, obviously 30% of the time it's going to be red, and they're the people whose bags you're checking. So out of like 100 bags, you're going to be checking 30 of them, okay? So what they did was they actually did like a simulation of this and kept track of people coming through, hitting the button, and what color light they got, okay? And that's what you see there on the middle of page 566, okay? So what they did then at the bottom, so they were trying to, it sounds like they were trying to test, you know, is it really 70% of the time that it turns green? Maybe they have reason to doubt that for some reason. If you were to read the rest of the paragraphs there, you'll see, you know, I'm trying to, just to save you time, gloss over it a little bit. So what they're describing the statistic p hat to be, is, let's see, so oh, they actually did like a random digit table. Okay, so you know 70% turns green, so if you use the digits 0 to 9, 0, 1, 2, 3, 4, 5, and 6 are going to be a green light because that's 7 digits. Then 7, 8, and 9 are going to be a red light, and they're the ones who are going to get stopped for inspection. So they actually did like a simulation via a random digit table, it sounded like. So every digit they pick simulates a person coming through, and depending upon what that digit is, that tells us whether the person got a red light or a green light. Okay, so the first person who came through was a number 1. Okay, so that's a green light. Second person that came through had number 9, so that's a red light, so they're going to get stopped. And then the next 3 were green lights. Okay, and then they did it, so they have all together, so they got 20 here, I guess. It looks like 5, 10, 15, 20. Okay, so out of those 20, they could figure out how many actually got red lights as opposed to green lights. So let's see. So how many green lights do we have? 1, 2, 3, 4, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15 out of 20. Okay, so what's 15 out of 20? So in this case, with this sample, if I'm just using the 20 that are there, so 15 out of 20 people got green lights. That's 75%. So that's higher than they thought. Okay, so what they would do is pretty much repeat this over and over and over. All right, and that's what you see in the histogram below. All right, and you can see the way in which the histogram's composed. On the horizontal axis, we have the proportion, and the vertical axis, we have the count of 1,000 samples. So how many in a sample of 1,000, you know, how many times did it work out? So they did a heck of a lot of samples, basically. Okay, we just did that one with those 20, and we got a percentage of 75. So that's going to be like right down there. If you look in between 0.73 and 0.76, that's going to be where we just fell with that one single simulation they showed. But take a look at how it looks, though. All right, and this is something, again, that we've been sort of talking about, is that with repeated sampling, and we've been talking about normal distributions, it should happen that with repeated sampling, your distribution becomes approximately normal. Now, again, you need a heck of a lot of samples before you might see that happen. And I think this is a great example of that. Okay, you can't just maybe do a couple and expect it to work out. Right? You need a lot of samples before that pattern manifests itself. Again, an idea that we've really talked about. All right, so let's take a look at one of the problems. If you flip over to page 568, this is going to be similar to one that you'll be doing for homework. This is number 9.1. You'll be doing 9.2 for homework. And all they ask you to do is state whether, if you take a look at the italicized directions there at the bottom of the page, they want us to state whether the value that's in boldface is a parameter or a statistic based upon the definition, and then use the correct notation to describe it. So if it's a proportion, you're going to use P. If it's the proportion from a sample, though, it'll be P hat. If it's a mean of a population, you'll be using mu. If it's a mean, though, of a sample, you'll use X bar. So that's kind of what they mean by that. Okay? All right, so letter A. So the ball bearing in a large container has a mean diameter of 2.5003 centimeters. This is within the specifications for acceptance of the container by the purchaser. By chance, if you continue to the next page, an inspector chooses 100 bearings from the container that have a mean diameter 2.5009 centimeters. Because this is outside the specified limits, the container is mistakenly rejected. So this one you really have to think about. Because they're talking about ball bearings in one large container, and then they're choosing 100 from the container itself. Okay, so the 2.5003 value, hopefully you agree, the way I read that, is that's pretty much what it's supposed to be. Okay, that's what the ball bearing is supposed to have. And they'd even tell you kindly it is a mean. All right, now on the next page, they talk about how the inspector then takes 100 bearings from that container. And the way I read that is found that the mean diameter was 2.5009. So I took that as like the X bar, the sample mean. All right, so this is, first one is the parameter. The second one is the statistic. Okay, hopefully that makes sense. All right, let's look at part B. So the Bureau of Labor Statistics last month interviewed 60,000 members of the United States labor force, of whom 7.2% were unemployed. All right, so out of the entire U.S. labor force, which has to be pretty darn big, they interviewed 60,000 members, and of those 60,000 members, 7.2% were unemployed. All right, well, it is a statistic. Because that 7.2% is only pertaining to, applicable to, those 60,000 people that were in the survey, not the entire population. All right, now it's not a mean. We're not talking about the average number who are unemployed. They're sort of just reporting a characteristic of those 60,000 people. So this one would be a proportion, and since it's just really of the sample, we refer to it as p hat. And that was the only bold-faced one in that problem. Okay, so as I said, this is very similar to numbers 9.2 that you'll be doing for homework. And there are some other ones you'll notice. Let's see, this was going to be another one. Some of these we are going to save because some of these are simulations that I sort of want us to do together, then like pull together our results. So some of these other ones that I have, we're going to come back to, okay? So like 9.11, that's another one we'll do when we all come back together. Actually, we can do that one now. That's sort of like 9.2. We can do this one if you want. If you want to flip over to page 579, it's the same directions. They just want us to state if it's a parameter or a statistic, and then use the correct notation. Okay. So this is dealing with small classes in a school. So the Tennessee STAR experiment randomly assigned children to regular or small-sized classes during their first 4 years of school. When these children reached high school, 40.2% of blacks from small classes took the ACT or SAT college entrance exams. Only 31.7% of blacks from regular classes took one of these exams. All right, so you have to first of all think about, all right, are we talking about a value that characterizes just a sample, which would cause it to be a statistic, or is it characteristic of the entire population? So I guess in this case we're talking teenagers, or maybe just people in the experiment. All right, so both of these are statistics. The reason is we are only talking about one particular segment of children that participated, specifically black children. It sounds like maybe they were looking at it by race, perhaps, I guess. Had they been describing all the kids who were in the program, then we could maybe think about it as the population being all children who participated in this experiment. All right, so again, we're not talking mean, like average number of people who took the SATs. Both of these are going to be p hat values, proportions. And that's really all they wanted to do for that one. Okay. So let's talk about describing sampling distributions. And you'll probably be thinking, haven't we been talking about this? Yes, you have. So this should not be anything new. Yes, we are once again talking SOX. And just as we used SOX as an acronym of what to keep in mind when we analyze data, we can do the same with sampling distributions when we're trying to take a look at a visual of a sampling distribution. As we've seen before, haphazard sampling does not give regular and predictable results. We talk about random sampling. Random sampling we know is good. Random does not mean haphazard, like chaotic, out of control. Okay, random, we've talked about how to correctly do a random sample. Whether we're using like maybe the random number generator in our calculator or the random digit table, there's a difference between random, which is good, and haphazard, chaotic, out of control, which is not random. Okay, that kind of sampling that is haphazard or out of control or not done well will not produce regular and predictable results as we want it to. But if we do correctly randomize and randomly collect our samples, statistics from the data should have a definite pattern of behavior in the long run. All right, again, an idea that we've talked about repeatedly. All right, so another thought. Again, sort of something like stuff we had talked about before. Bias. We talked about bias as, Unit 1? Yeah, we did. All the way back then. Now we're specifically talking about bias of a statistic. And when we talk about bias of a statistic, what we're really trying to answer is that very first question you see here. How trustworthy is a statistic as an estimate of a parameter? So let me give you an example. Big population. Maybe we want to know the mean income for a family of 4 in the United States. Obviously, we cannot poll every family of 4 in the United States. So we're going to have to take samples. All right, maybe we go by state and we take maybe 100 such families out of every one of the 50 states in the United States. All right, that would be a way to randomly generate some data. All right, but the question is, all right, if we were to do that, how certain and confident can we be that like the little X bar values we get out of those samples, how well are those going to reflect what really is true about the entire population? So what we can talk about is really the bias of a statistic rather than a bias in a sampling method. And that's the part we had done back in Unit 1, is we had talked about bias in a sampling method. All right, and we talked about some bad sampling methods, you might remember. So this is somewhat related to that, because we are still talking sampling. But now we're really talking about the bias of the statistic that we generate itself. And one thing to keep in mind is that bias really is going to concern the center of the sampling distribution. Now, if that sampling distribution is approximately normal, remember at the center you're going to have the mean, which should equal the median. Okay, so when we talk about the bias involved in a statistic, what we're really talking about is seeing how it affects the mean or the median of that sampling distribution. Now, as you can imagine, we don't want bias if we can avoid it. And a statistic used to estimate a parameter is considered to be unbiased if the mean of its sampling distribution, is equal to the true value of the parameter being estimated. So this is if it was means. If we were talking proportions instead, it would be if p hat equals p. This is a big idea. Keep that in mind. All right, so of course we want a statistic to be unbiased, meaning in normal English, we want that statistic that we've generated from a sample to be reflective of what is really true about the entire population. And if that is the case, that the statistic really does reflect what's going on with the entire population, that's when we can say that the statistic is unbiased. Okay. Another idea. Now remember, the goal here was kind of just to get all the notes out there, and we're going to come back later and kind of delve into this a little bit more and do some more practice. Okay, this is just really making sure you have the notes. You might have to come back and think about it a little bit later on. Hopefully the homework problems that I'll give you will enable you to do that. So another idea that we're going to talk about is the variability of a statistic. Visually, that's what's going to be given to us by the spread of the sampling distribution. And one thing that we've seen is that if we have a larger sample, that generally will yield a smaller spread. All right, the reason is, we talked about if we have a larger sample to draw from, that's generally going to result in less variability. We saw that even back in Unit 1 as well. You might remember me saying, and the day is coming when you learn that equation as to how do you know how big of a sample you need so as to get as little variability as you can. And the next bullet actually gives you one little guideline that you can use. It's not the actual formula. We'll have the formula later. But one rule of thumb is that as long as the population is at least 10 times as large as the sample, the spread of the sampling distribution should be approximately the same for any population size. So one rule of thumb that we'll often use is we want to make sure that the population is at least 10 times as big as our sample. All right, so what that means is that the variability of the sample results is sort of controlled by the size of the sample. Which hopefully that makes sense, because we just said that larger samples are going to yield a smaller spread, less variability. So I'm hoping this first bullet makes sense. The variability that we're going to see is almost going to be a byproduct of the size of the sample. The interesting thing, the size of the actual population really has very little influence on the spread. It's all dependent upon the size of the sample. That's something they often turn into a multiple choice question. All right, so really the part you want to keep in mind is that the variability that you're going to see out of a sample really is a byproduct of the size of the sample itself, not the population. It has nothing to do with how big the population is. All right, and the last thing we're going to talk about, you'll definitely need your book for this because we'll be referring to some diagrams there, is the whole idea then of how bias and variability tie into each other. Because they are two very different characteristics of a statistic. And one really great visual that is pretty popular in statistics is the one that you're going to see on page 576, if you would turn to that. And it's the analogy of like a bullseye. Hopefully you're familiar with a bullseye. If you were to read the paragraph at the very top, I'll try to summarize it for you. So imagine taking a lot of shots at the target, at the bullseye. Depending upon where you hit, that could tell us something about the bias and variability. All right, and if you read at the very top, I'll see if I can kind of copy this over. The bias part, that's like, how good of a shot are you, basically? So the bias refers to, was our aim off? How close to the bullseye were we? The variability, as you can imagine, is kind of like how consistent are you in terms of where your shot strikes the target. So the variability kind of talks about like your consistency. All right, and if you go back later and read that top paragraph, it actually does a pretty good job explaining it. Okay, so let's take a look at the 4 pictures there. Okay, the bullseye itself, the entire round bullseye, think of that as the true, or the bullseye in the center, I guess. Okay, like the target. Of course, assuming you guys know anything about target shooting, you're always trying to hit the center. Okay, so that's what we refer to as the bullseye in the very, very center. Okay, think of that bullseye as the true parameter of the population. So whether we're talking like a mean or a proportion, it doesn't matter. Okay, so think of this bullseye at the center of the target. That's your true parameter of the population. That's what you're trying to get. That's what you're trying to hit. That true population parameter. So every shot you take, that's your sample statistic. Okay, so take a look at the one in the upper left. Okay, notice how they're all nicely clustered together. Okay, so in terms of consistency, in terms of you shooting, you're very consistent because all your shots are very nice huddled together. So that means we have low variability because your shots are at least really packed together tightly in relation to each other. Okay, so that's low variability. But notice how you're pretty far from the target at the center. That's high bias. Okay, so you didn't really come close to the bullseye at all. So that's high bias. But the fact that the shots you did take are all nice and clustered together, very consistent with each other, that means you had low variability. Okay, so think of it, like I said before, every sample you take is like a shot you fire at the target. Okay, and the sample statistic of mu or p are going to be our population parameters. Obviously, we're talking about, x bar or p hat as being our sample statistics. All right, now look at the one on the upper right. the one that's labeled B. All right, notice how they're like all over the place. Okay, so you shot and you kind of like hit a different place every single time you shot. That's high variability. You're very inconsistent. Your X bars that you gathered really have no consistency at all. They're all over the place. All right, but some are pretty close to the center and hitting the mark of that true population parameter. So that's why we consider it low bias. Okay, so the fact that your shots are all over the place, your X bars or your P hats are all over the place, that's high variability. But the fact that at least some of them are sort of kind of close to the center and your target of the population parameter in the middle, that's why we would consider it low bias. Now maybe you'd consider it maybe like medium bias. I maybe would call it that. I don't think it's really, really low bias. I think it's like medium. All right, now look at the one on the bottom left, the one that's labeled C. Okay, really far from the target. You're nowhere. You're off the board, really. That's high bias, nowhere near the center. And your shots are still kind of like all over the place. You know, they're not, you know, yeah, actually they are kind of all over the place. They're not nicely packed together like the first graph was. So this is one that's going to have both high bias and high variability. Then the one on the lower right, that's the one that we would like to see. All right, obviously you're hitting the bullseye every time. That means every time you gather a sample, your statistic, your X bar or your P hat is very closely approximating what the true population parameter is. That's what we want to see. That is low bias. And the fact that when you did it over and over and over, they're all nicely close together, that's low variability as well. That's what you want to see ideally when you do create a sampling distribution. So really what should happen is if you were to properly construct your samples and have a sufficient size, according to the guidelines that that one that we just mentioned, that you want your population to be at least 10 times as big as your sample, and other rules of thumb that we'll be talking about coming up. Assuming all those, ducks are in a row, okay, and you can make sure you tend to all that stuff, it should work out that your sampling distribution will have low bias and low variability. All right, and that's, if you think about it, that's kind of what we've been talking about since our very first day together, is how to correctly and properly do a survey, construct a sample, do an experiment. Okay, this is really just feeding off of that idea. Okay, so hopefully you can digest that. And if you need to come back and look at the pictures, that's not a bad idea to do that. And that might be a good place to stop. Oh, this is what we've just talked about, sorry. All right, so high bias means, remember, you were really far from the middle. All right, aim totally off. High variability, your shots are all over the place. They're very inconsistent. All right, so I think that should be the end of your notes on your handout. So as I said, the rest of the problems we're going to save, like these that you see here, we're going to save till we come back. Maybe I'll even save this whole PowerPoint and just use the same one. I'm just going to give you a few to do, kind of just to make sure you sort of got the gist of the basic notes, okay? So they start on page 569, and they go over to about 580, and there's just 3 of them, and they're all just like the ones we did today. 9.2, 9.10, that's going to deal with that, low bias, low variability idea. And then 9.12. If you would just do those 3, they are very, very short. Just again to make sure you got the gist of the notes, okay? When we come back together, remember your quiz is supposed to be Thursday, January 30th. If you're in school, you will be taking the quiz, okay? If by chance we're off again, but then we're back in school Friday, you will take the quiz Friday. All right, please just keep checking your email, okay? Because I will be in touch. If you have any questions at all, just email me. I'll be checking email very, very consistently, okay? But thank you for taking the time out of your snow day off to watch this. That should really, really help. And it will make me feel better, so I'm not going to lie. Okay, so enjoy the rest of your day. Thank you again for watching, and hopefully I'll be seeing you real soon.